If we have a model that's going to make predictions, there are two different types of predictors. There are classifiers and there are regressors. It's important to be able to differentiate between the two. A regressor is a model that will predict a continuous value. Think of it as you have a model, you want to predict a home price. Well, that's a continuous value. So you want to work with a predictor that is a regressor. A classifier, as the name implies, is a model that's going to predict classes, going to predict discrete categories for your observations. For example, let's say you're trying to train a model that, given an image, will tell you whether the image is a pipe or not a pipe, a cat or not a cat. In that case, you're not trying to predict a continuous value. Instead, you're trying to predict a class for your observations. So depending on what you're trying to predict, you would either use a classifier or a regressor. And that kind of breaks down the two main branches of supervised machine learning. Are you working with regression or you're working with classification? Now going back to scikit-learn, when you've created an object from a class that represents a predictor, let's say we want to train that model, or we want to fit that model given a data set, X and Y, the observations with the characteristics and attributes along with the labels associated with all our observations. Going back to this setup we have here, our X and Y. Because remember, we're trying to train a model F, figure out a model F, such that given observations X will predict the values Y. In this example here, we're going to use linear regression. As the name implies, it is a regressor. It's going to import that class. Let's construct an object from that class. That's what we do in this line. Let's go ahead and fit the model. So we're going to fit with X and Y. So this is going to fit and train the model. So it's going to figure out what are the best set of coefficients, model coefficients it should use. It's going to best fit the data set. And then once we have our model that has been fitted or trained, we can use that model to make predictions. And that is all done with the predict method. So when we're working with predictors, the two key methods are fit and predict. And of course, you cannot predict before you have fit the model. In fact, if you try to, you'll get an error message that says, I believe you get a not fitted error message. Alright, so to do things properly, so this is going to fit the model with X and Y, and then once we fit the model, we can make predictions. So we're going to pass, when we make predictions, we simply need the set of observations. We don't need the labels because that's what we're trying to predict. Alright, so we're also going to print out the resulting labels in the shape of the predicted values and our data set X. So we run that, and notice the values are returned as a NumPy array. So we can just verify that for. Let's go verify that. I know it looks like a list, but in fact it is a NumPy array. So I'm going to just use the type function, get the data type, and it's a NumPy array. Looking at the shape, we notice that we have predicted over 2,000 values. And that makes sense because if you look at our data set that we use to make the prediction, this X here, we look at the shape, it indeed had 20,640 rows. In other words, 20,640 observations. So we call the predict method on X, we get a predicted value for each of those observations. Notice these two dimensions match. The size of those two dimensions match, so that's good. Okay. Now let's delve a little deeper. So we've trained a model. Sometimes we want to inspect some of the model's attributes after we have fit it. So for linear regression, what we are essentially doing is that there is a coefficient associated with each feature, each characteristic, each attribute of your observations. If you recall, there are a total of 8 characteristics, 8 features for your observations. That was back at the very top when we looked at the description of that data set. There they are listed. So what linear regression model is doing is that we're saying there's a linear relationship between each feature and the predicted value, the value you're trying to predict, the y, the target, the label. So we can actually, for linear regression, it's a rather simple model. We can write it all out. So this essentially is the model we're using. And then when we call the fit method, what's happening behind the scenes in scikit-learn, it's looking for the best set of these beta coefficients, the coefficients associated with each of the features. What are the best set of those values that are going to best fit the data? We'll talk more about linear regression, how it figures out the best fit line, what kind of metrics it's using. But at the moment, just consider that behind the scenes, the algorithm is trying to figure out what are the best beta coefficients to have to best fit the data. So afterwards, it might be very important for us to analyze and look at these beta coefficients. We want to know what are their values. That might tell us some insight, might give us some insight to what the model is doing, how the model is weighting those characteristics, those features. So since these beta coefficients, we only know them after we fit the model, after we train the model, they're going to manifest itself as attributes of the object, and scikit-learn is going to take the convention that their name ends in an underscore. So if we're curious to see what is the value of beta naught, the intercept, we would do simply model dot intercept underscore. So that will give us the intercept for the model. Regarding the coefficients, those are stored as a NumPy array called coef underscore. So let's run this line here, this block here, and there are the resulting coefficients and intercept for our model. Now notice these attributes, intercept and coef, only belong to the linear regression class. There might be other models that use these same variable names, but other models will have different attributes depending on what type of model it is. You might be running, okay, well, can I look at maybe a list of these attributes to figure out what's available for me to inspect? No problem. We can open up the documentation for our model. So that's what I type in here, linear regression. In Jupyter Notebook, if I put a question mark at the end, if I run this line here, it will pull out the doc string, the documentation string for how to work with this variable. So let's go ahead and do that. There we go. We look at it. This is a signature. In other words, when we create an object from this class, these are some parameters we can pass. So these are some hyperparameters when we can view it that way. If I scroll down, I have the parameters. If I scroll further down, the attributes. There you go. So these are the attributes for that object. I'm going to tell you the description. So notice here, this coefficient will be a shape of n number of features, or n targets versus n number of features. So it's a coefficient that is associated with each feature in our training set. So make very use of looking at the documentation. As I said before, we're not expecting you to memorize all the different attributes an object has, these models have. You should, of course, be familiar with some of the basic ones, some of the more important ones, but be comfortable enough to look at the documentation and see what is going on. And read the documentation, figure out what do you need for your purposes. Okay. There is additional method with this object called score. And of course we want to understand, okay, well, how well does our model perform? So to evaluate how well our model performs, we need to give it a data set to investigate, not investigate, but necessarily like, okay, predict these values for these observations, and we have to have the answer. So what's going to happen is that we give it a data set X. It makes predictions on all those observations. We want to compare it with the true values and use a metric that tells you how well the model performed. That can be all achieved by using the score method. You pass it two parameters. You pass it the data set X, the data set with the observations and the features for each observation, along with the true values y. So underneath the hood, what's happening when you call this method of this object, it's running predict on x, taking out those predicted values, comparing it with the true values you passed, and using some metric to devise to figure out how well the model performed. In this case, it's going to report out the r-squared value if it is a regressor. We'll talk about more what this r-squared value represents, but you want a model to have as high as an r-squared value as possible, close to 1. So if a model is able to correctly predict the true value for a set of observations, it will have an r-squared value of 1. Having an r-squared value of 0 implies or suggests that your model does just as well as a model that always predicts the mean of the data set. So it's a sort of a naive benchmark. You can compare how well your model performs. You should want your model, of course, to have an r-squared value greater than 0, and typically it will, but it is possible to get an r-squared value of -1. We'll talk about more about this metric when we talk about linear regression, but that is the metric it uses for regressors. For classifiers, it's going to report out the accuracy, which makes sense because when we're dealing with classification, we want to understand whether an observation was accurately predicted to belong to the correct class. In other words, given this image that is not a pipe, was our classifier able to correctly predict that in fact indeed was not a pipe? So the value, the metric you get out when you use score for a classifier is simply the accuracy. We'll talk more about specific metrics you would use for classification and regression because they do differ in the appropriate notebooks. But keep in mind, the score is a way you can evaluate how a model performs given a data set, and the labels the true values for that data set. So for this example, let's see how well our model works. So we see we have an r-squared value of about 0.6. So that's decent, I guess, for a rather simple model. So what if we wanted to use a more complicated model? And of course, we won't discuss what's going on with this more complicated model. This is just to more show you that simple, nice interface scikit-learn uses. How we can easily swap out a model and replace it with a different type of machine learning model. And this code that we have written doesn't change that much. So for example, here we're going to use a model called gradient boosting regressors. It's a model that is rather adaptive, that has a lot of predictive ability. So let's go and import that class that represents that model. Let's create an object from that class. In order for us to fit and train that model, it's the exact same syntax. We use the fit method of that object. Pass it x, pass it y, it's going to fit the model. Once the model has been fitted, then we can use it to make predictions, and guess what? We use the same method, the predict method of that object. So the exact same interface. The only thing that will differ is that when you construct this model here, there might be different arguments you pass it when you create the object from that class. All right, so let's go ahead and also predict out the score value. See how well it does, and it looks like we have an r-squared value of 0.8. So it does a better job at predicting the true values with the training set, the data we use to train the model. Now you might be wondering what other parameters I could have passed when I created the gradient boosting regressor object. I can look at the documentation. If I look at parameters, these are all the parameters that I can tweak or change when I create an object from that class. And these are the hyperparameters to the model. Now when we talk about gradient boosting regressors, we'll talk about these different hyperparameters, but usually scikit-learn is pretty good about using a nice set of default values for these hyperparameters. They're usually good. It tries its best to use ones that will typically work pretty well straight out of the box, but of course you should look at the documentation, see what's available for you to tweak, and think about how you should tweak them in certain ways, or how you go about best tweaking those values. So let's not get too muddled up with the details about these specific models. The whole point behind this part of the lecture is to show you that standard interface, that standard application program interface when we are working with scikit-learn. We construct an object from a class that represents a model. We call the fit method when we pass x and y. And then once we've fitted the model, once we've trained the model, we can use the predict method to make predictions. And that third method called score, which evaluates the model given a data set X and given the true values Y.